Imagine a machine that can hover like a bird in midair, defying gravity with effortless grace, then suddenly surge forward, accelerating across the battlefield faster than many small airplanes, leaving a trail of dust and awe in its wake. Military helicopters aren't just flying vehicles. They're high-speed combat machines engineered for the most extreme missions imaginable. From rapid troop deployment in hostile territories to high-speed pursuit of enemy targets to surviving brutal combat zones riddled with enemy fire, these beasts must be fast, agile, and incredibly powerful, pushing the limits of physics and human ingenuity. But have you ever stopped to wonder, why are military helicopters so blazing fast compared to your everyday civilian choppers? The answer? It's a perfect storm of powerful engines, cutting-edge rotor technology, and smart aerodynamic wizardry. Today we're diving deep into the engineering secrets that transform military helicopters into some of the fastest rotary wing aircraft ever built. Buckle up, this is going to be an exhilarating ride through aviation's front lines. The heart of the beast, power-packed engines. Everything starts with the engine, the throbbing heart that gives these machines their raw power. Unlike the piston engines in most civilian helicopters, which chug along like reliable pickup trucks, military helicopters roar to life with high-performance turbine engines. These bad boys are cousins to the jet engines that propel fighter jets and airliners. Picture this: they gulp down aviation fuel, ignite it in a blazing inferno, and produce extremely hot, high-pressure gases expanding at supersonic speeds. These gases blast through turbine blades, spinning them thousands of revolutions per minute, like a 1,000,000-horsepower fan on steroids. That rotational fury gets funneled through a heavy-duty gearbox, which multiplies torque and spins the main rotor blades with ferocious speed. The result? Massive, overwhelming power, often 2-3 times what a civilian helicopter needs just to hover lazily over a traffic jam. Take the AH-64 Apache, for example. Its twin T700 turboshaft engines crank out over 3,800 shaft horsepower combined. That's enough to hurl this 15,000-pound attack helicopter from a standstill to over 300 kilometers/miles (HU), over 300 kilometers/h in seconds, dodging missiles while raining hellfire on targets below. This surplus power isn't wasted. It's the key to explosive acceleration and top speeds that make pilots grin ear to ear. Civilian helos, they're built for comfort and short hops. Military ones are bred for warzone sprints. The spinning wings, rotor blades engineered for speed. Now let's zoom in on the star of the show, the rotor blades. These aren't just props, they're spinning wings slicing through the sky. As they whirl overhead, they act like an enormous fan, slamming air downward to create lift. It's Newton's third law in action. Push air down and the helicopter rises up. Simple, right? But for speed, military engineers redesign these blades from the ground up. They're longer for more bite into the air, stronger to withstand brutal forces, more aerodynamic with twisted airfoil shapes that slice drag like a hot knife through butter, and crafted from advanced composite materials like carbon fiber and Kevlar. Why composites? Steel blades from the old days were heavy and brittle. They'd snap under high RPMs. Modern ones are feather-light yet tougher than tank armor, letting them spin 20 to 30% faster without shattering. Faster spin equals more lift, equals screaming forward speed. Consider the Eurocopter Tiger. Its free turbine rotors, made of glass and carbon composites, let it dash at 290 km/h while pulling 3G maneuvers. These blades flex just enough to absorb shocks, but stay rigid for precision control, pure engineering poetry. Tilting into the wind, the magic of rotor. Tilt and forward flight. One of the coolest tricks for forward speed is rotor tilt, a bit like leaning into a bike turn, but in 3D. In hover mode, the rotor disc, the circle the blades trace, sits flat, shoving air straight down. Want to bolt forward? The pilot tweaks the swash plate, tilting the entire disc 5-10 degrees ahead. Now, that downward blast gains a backward component. Physics kicks in. For every action, there's an equal and opposite reaction. Air shoved back propels the helicopter forward like a swimmer pushing water behind them. With military-grade engine power, pilots can tilt aggressively, converting 70 to 80% of lift into thrust. The CH-47 Chinook transport helicopter exemplifies this. Its tandem rotors tilt forward under 10,000 horsepower, hauling 50 troops or artillery at 315 km/h. No fixed wings needed, just smart tilt and brute force. Sleek as a shark, aerodynamic mastery. Military helicopters don't just rely on rotors, they're sculpted for speed like Formula One cars. Forget the boxy, draggy shapes of civilian workhorses like the Bell 206. Combat helos boast sleek fuselages, tapered noses, and flush rivets that let them knife through the air. This slashes drag by 30 to 50%, turning potential energy into pure velocity. Many pack stubby wings, too not for flying like planes, but for high-speed lift. At 250+ kilometers lash, these wings unload the rotors, letting blades focus on control rather than all the heavy lifting. The result? Smoothing, faster cruise with less vibration. The RH-66 Comanche stealth chopper took this to extremes. Radar-absorbent composites, retractable landing gear, and a needle-thin profile for 325 kilometers/EHs, silent and deadly. Breaking barriers, advanced rotor system speed kings owe their edge to innovative rotor setups that cheat traditional limits. Rigid rotors, like on the Apache, lock blades stiffly to the hub, handling wild G-forces without flapping wildly. Fully articulated systems add hinges for smooth flex, reducing stress at Mach speeds. Then there are compound helicopters, hybrids with pusher props or jets. The Sikorsky X2 uses coaxial rotors, 2 stacked counter-rotating sets, plus a pusher prop, smashing 460 kilometers/h faster than most props planes, while hovering like a hummingbird. Experimental beasts like the Cartercopter tilt rotors and slow them mid-flight, hitting 502,000 slow them mid-flight, hitting 520 kilometers/h without blade tip woes. The speed demon's curse, retreating blade stall. But speed has a nemesis, the retreating blade stall. Helicopter blades advance on one side toward flight direction and retreat on the other. At 300 kilometers/h, retreating tips lag, stalling airflow and causing asymmetric lift roll, shake, kaboom. Tips near Mach 1 spawn shockwaves, spiking drag and noise, that signature whop whop. Military fixes? Slower main rotors paired with tail props, swept tip blades, and active vibration control. The record? Sikorsky's XH-59 at 443 kilometers/h in 1986, edging toward the rotary limit. Tech arsenal, military-only innovation. Civilian helos dream of these upgrades. Advanced composites, 40% lighter, 2x stronger. Twin turbine engines, redundancy for battle damage. Fly-by-wire systems, computers predict and stabilize chaos. High-strength titanium hubs endure 20,000 RPM torture. These let helos skim treetops at 200 kilometers/snake through valleys, or evade SAMs with split-second jinks. Speed equals survival. Legends of speed, real-world speed demons. Mi-24 Hind, Soviet tank killer, 335 kilometers west Troop Bay. AW-159 Wildcat, naval hunter, 319 kilometers/agility. Prototypes like Sikorsky Raider X, aiming 500 kilometers lash for future vertical lift. Each era ups the ante. The horizon, tomorrow's Sky Warriors. The future, helicopters morphing into plane helo hybrids. Tilt rotors like the V-22 Osprey, swivel props for 565 kilometers/fuselaje, BTOL anywhere. Coaxial plus wing designs promise 500+ kilometers/h. Electric motors and AI flight controls will slash noise and boost efficiency. Imagine Delhi skies filled with these vertical takeoffs from urban pads, supersonic sprints to borders. Outro, engineering's ultimate triumph. So next time a military helicopter thunders overhead, racing the horizon, remember, its blistering speed isn't luck. It's decades of relentless innovation, from turbine infernos and composite blades to tilt physics and stealth aero. These flying fortresses embody aviation's pinnacle, and as engineers shatter limits, tomorrow's helos will hover, hunt, and haunt the skies like never before, faster, fiercer, unstoppable. What an era to be alive. Like, subscribe, and drop a comment. Which military helicopter blows your mind most?
This cross-section shows a helicopter rotor's airfoil shape. Airflow over the curved upper surface is faster, creating lift. The camber line defines the shape's asymmetry, essential for performance. This diagram shows an airfoil. As it rotates, air flows faster over the upper surface, creating lower pressure and lift. See the vortex shedding here? That's causing the instability.
Right. We could adjust the pitch to smooth that out.
Good idea. Let's check the prototype.
Okay. The new materials should help.
Let's check the simulation. We're aiming for better efficiency.
Okay. I've got the new blade pitch data.
Good. Let's input it in sync.
Okay. It's working. Efficiency is up to 85 improvement. These advanced composite blades are designed for maximum efficiency.
Impressive. Let's see them in action.
Watch how they flex under load. This reduces vibration and extends life.
This prototype is built for high-speed tactical maneuvers.
Let's see it in action.
Initiating ascent and evasive turn.
Look at that agility.
Descending now, touchdown.
Perfect stability.
This model is the prototype for our simulation.
It's spot on. Let's test the aggressive turn.
Initiating the turn now. Compensating. Turn is holding at 45 degrees. What a beautiful day for flying. Descending now, check out that sunset. Look, a heliport flying across the horizon. Perfect timing.
Control, this is Eagle 1 on Fun Ranch. Eagle 1, your OK lands on helipad 2.
Cleared to land, helipad 2, beginning descent. Copy, Eagle 1, ground teams are standing by. Engine temps look stable, opening the cowling for a visual. Intake is clear, no visible damage to the blade, all clear for now. Fan blades look clean, no visible cracks. Copy that, check the intake seals. Seals are good, no leaks. All right, let's secure the panel. Panel secured, good to go. Panel secure, initiating spin test. Copy, accelerate to 1500 RPM. RPM stable, vibrations within limits. Good, check the blade pitch sensor. Sensor nominal, test complete. All systems optimal, you're clear for takeoff. Roger that, starting her up, copy, safe flight. Powerful turbine engines and advanced rotor design make military helicopters incredibly fast.